So welcome to the lecture on critical speed of shafts. So in this lecture we will discuss about the critical speed of multi-rotor shafts. So in the previous lecture we discussed about the critical speed of a single rotor light shaft. Now if we have more than one rotors on a shaft or more than one disc on a shaft, so how to find the critical speeds of the shaft? If we have two rotors, we will have two critical speeds. So there will be as many critical speeds as the number of rotors on the shaft. So let's consider a two rotor system. So here we have a shaft and it is vibrating, and here is two rotors, and during the vibration there is the displacement amplitude y1 and y2. So here so we have this shaft so we have this shaft, and so we have this bearings. Here we have bearings, and we have two rotors on this shaft. Now suppose this shaft is vibrating, so we have this configuration. And this is the position of our rotors, and this is the position of our rotor. So we assume that the shaft is light, and the rotors have some eccentricity between their geometric axis and the center of mass. So here we have, let's say, this G of this first rotor, and here is the G of that is the center of mass of the second rotor. So this is y1, this is y2, and here it is E1, and this is E2. So eccentricity between the center of mass and the geometric center. So y1 and y2, they are the deflection of two rotors or two discs from the center line of the bearing, from center line of the bearings. So here we have, this is the center line of the bearing. So we have y1 and y2, and then from this y1 there is E distance, radial distance, there is the center of mass, and here for the second one it is E2 distance, the center of mass. And here the mass of the first rotor is m1, the mass of the second rotor is m2, and these are the centrifugal force F1 and F2 acting on these discs. So these F1 and F2 are the centrifugal forces. These are the centrifugal forces on the two rotors, respective rotors. So here now the centrifugal force, we know that it is m or omega square. So m, that is for one m1 into omega square into r. So r is here y1 plus e1. So y1 plus e1 for the first rotor or first disk, and F2 is the centrifugal force on the second rotor. So it is m2 omega square y2 plus e2. Now this y1 and y2 we can also write with the help of flexibility influence coefficients, and flexibility influence coefficients are defined here. Flexibility influence coefficient is defined, that is Aij is defined the deflection at point I due to a unit load applied at point J. So if I say A11, if this is 1 and this is 2, so this point will have deflection due to this force as well as this force. So A11 means deflection at 1 when unit load is applied at 1, and so the total deflection will be A11 into F1, because A11 is the deflection due to unit load, and into F1, so the total deflection due to the force acting on this position. Now if I say A12, so this is the deflection at 1 due to the unit load applied at 2. So the total deflection will be A12 into F2 at this, and this total sum will be Y1, and similarly for the second rotor. So here if I say Y1, so Y1 equal to A11 F1 plus A12 F2. Similarly, so this will be the total deflection Y1. Now Y2 will be equal to A21 F. So deflection at 2 due to unit force at 1. So total force F1 at 1 plus A22 into F2. So this is the Y1 and Y2. Now we can rewrite this as Y1. So because we put the values of Y1 and Y2 in the expressions, so Y1 equal to A11 M1 omega square Y1 plus E1 plus A12 M2 omega square Y2 plus E2. So this is expression, and second expression Y2 equal to, so we are putting the values of F1 and F2 and we are writing the expressions. So 81 M1 omega square Y1 plus E1 and plus A22 M2 omega square Y2 plus E2. So here we have written these expressions. So we have replaced the force F1 with the centrifugal force and F2 with the centrifugal force at 2. Now when we talk about the critical speed, because here we want to obtain the critical speed, so at critical speed the y1 and y2 are quite large, because here omega we want to find as a critical speed of the shaft. So in critical speed condition, y1 and y2 are much larger than e1 and e2. So in these expressions we can neglect e1 and e2 with respect to y1 and y2, and we can rewrite these expressions. So y1 equal to a11 m1 omega square y1 plus a12 m2 omega square y2. Similarly here y2 equal to a21 m1 omega square y1 plus a22 m2 omega square y2. Now we can arrange these terms. We can take these terms to arrange y1 and y2. So a11 m1 omega square minus 1 y1 plus a12 m2 omega square y2 equal to 0, and then a21 m1 omega square y1 and plus a22 m2 omega square minus 1 y2. So this we can write as determinant. So a11 m1 omega square minus 1 and a21 m1 omega square. Then here it is a12 m2 omega square and a22 m2 omega square minus 1. So this determinant should be 0 to satisfy this equation, and from here we can solve for omega, and when we solve for omega, so omega square equal to p minus plus root p square minus 4q upon 2q, where p equal to m1 a11 plus m2 a22 and q equal to m1 m2 a11 a22 minus a12 square. Here a12 is equal to a21. So influence coefficient a12 is equal to a21. So we can see this expression. So because this expression we have obtained omega for critical speed, assumption of the critical speed, and so here we see that there is omega square, so we will get two positive values of omega. So when we take the negative sign, we will get the lower critical speed, and when we take this positive sign, we will get the second and that is higher critical speed of the shaft. So here this method, using this method we can find the critical speed of multi-rotor shafts. So here we can see the shaft is in the vertical plane. Now if the shaft is in the horizontal plane or the shaft is heavy, that is this shaft we assumed lightweight. If shaft is heavy, we have to consider also the mass of the shaft, and for this case I think the Rayleigh method is more useful. So now we will discuss this method, second method, that is Rayleigh method. So Rayleigh method is basically energy method that is based on the conservation of energy. So the total energy of the system for a conservative system remains constant. So here we are not considering the damping or dissipation of energy. We are considering the conservation of the energy, that is the kinetic and potential energy. So T plus U equal to constant, or T1 plus E1 equal to T1 plus T2, T1 plus E1 equal to T2 plus, so T1 plus E1 equal to T2 plus U2. Or we can say that the maximum energy, because maximum energies are the same, because there are points during the motion when the maximum potential energy is converted to maximum kinetic energy, and when one is maximum, other is zero. So in this condition, the T max equal to U max, and T max, that is the kinetic energy maximum, half mv square. So half mv is y into omega n. So y into omega n, y is the transverse deflection, and y omega n is the speed, critical speed. Then the potential energy is half mg into y, and considering for all disk we have the summation. When we sum these energy, we will get the total energy for the system. And these energy, so here we have the total kinetic energy, here is the total potential energy. So here this summation I equal to 1 to n. So if there are n rotors in the system, so we will get this m I yi square into omega n square equal to g summation I equal to 1 to n m I y I. So that expression we can write. So here we can see this is a horizontal shaft, and we have this deflection y1, y2, y3. So we can find the frequency of the natural vibration, because the frequency of the natural vibration is the critical speed. Because so if the shaft is rotating at a speed that is equal to the natural frequency or natural speed of the shaft or a rotor system, then this is the critical speed. So here omega n equal to, we will find g sigma I equal to 1 to n m I y I upon sigma I equal to 1 to n m I y I square. And we can also find the circular natural frequency. So this Rayleigh method is the second method, and there is another method that is called Dunkleys method. So this Dunkleys method, this method, when we have several these masses or multiple disks, so we have these forces due to the different disks. So the Dunkleys method says that we consider one load at one time and we find the natural frequency of the system, and that is easier. So if we have omega 1, omega 2 and omega 3, three rotors, and so there are three forces on this system, and there is also the this distributed weight considered for the shaft due to the self weight of the shaft, that is the distributed force. So first we consider W1, one single rotor, and we find natural frequency Fn1. Then we consider the second W2, and we find the natural frequency, that is second natural frequency Fn2. Then we consider the W3 and we find the third natural frequency, that is Fn3. So independently we are finding, just considering one mass or one rotor at a time. Then in the last we are considering the self weight of the shaft, that is a distributed type of load with W per unit load, and we are finding the natural frequency of this shaft. When we have found the separate natural frequencies of the system, natural frequencies of the system with separate rotors, then we can use the Dunkleys empirical formula, and it says that the natural frequency of the shaft when all the loads or disks act on the shaft simultaneously. So now we want to find the natural frequency of the whole system that when comprises all these omega 1, W1, W2, W3 or all these rotors and this. So this is our actual system, and so this actual system's natural frequency we can find by this formula. So that is 1 by Fn square equal to 1 by Fn1 square plus 1 by Fn2 square plus 1 by Fn3 square plus 1 by Fnd square. So this Fnd square, that is Fnd is the natural frequency when we consider the self weight of the shaft, that is the distributed weight. So here we see that we can find the multi-disc shaft or multi-rotor shaft. We can find the critical speed, because critical speed is nothing but the speed at which the speed of the shaft coincides with the natural frequency or natural speed of the shaft. And at this speed, the vibration amplitude of the system becomes quite large or very excessive, and therefore we need to find these critical speeds. And for multi-rotor system, we discussed these three methods. In the first method, we used the vertical plane, the shaft in vertical plane and lightweight shaft. Using the flexibility influence coefficients, we can find the natural frequencies of the system. For the other two methods, that is Rayleigh method. The Rayleigh method is based on the energy approach and conservation of energy, where we compare the maximum potential energy to the maximum kinetic energy of the system. And if there are n rotors, we have n the summation I equal to 1 to n. And from there we found the natural frequency of the system. Now this was the Dunkleys method. So this Rayleigh method and Dunkleys method, they are quite useful when we have to consider the mass of the shaft, and as well as the shaft is in the horizontal plane. So here we stop our discussion, and I thank you for attending this lecture, and see you in the next lecture.